All right, well, those of you who've spent time at Berkeley know that we have something that we call Berkeley time, which is that all classes actually start 10 minutes after, officially start 10 minutes after their official, the supposed time they're scheduled for. But it's always been, I've been here 12 or 13 years now, and I've never figured out whether Berkeley time also carries over to talks and meetings like this. So I think what I'm going to do is split the difference, and we'll get started. We'll get started now. It's about 5 past. So I'm Mike Franklin. I'm one of the directors of the AMPLab, and first of all, I want to welcome you to the first and hopefully first of many AMP Camp Big Data Boot Camps. I'll tell you a little bit about where this came from and set a little bit of the context. What I really want to do is tell you about the AMPLab, give you an idea. It's a pretty unique project, especially in an academic environment. So I want to tell you a little bit about that, and then we'll turn it over to the rest of the gang for the real technical meat of the meeting. All right. So I'm not going to spend a lot of time talking about big data, even though the program said I would. We all know big data is a big deal. That's why we're here. And you know, it's coming from all over the place, right? So click streams and all the stuff that we do online, generating just huge amounts of data, sort of at the user level, at the business level, at the equipment level, at the network level, everywhere. User-generated content, obviously another source of important information that we want to be able to make sense of. One of the challenges that people dealing with big data are facing is the ability to deal with large graphs. So whether it's you know, any sort of a network, physical network, like a road network or a communications network, or whether it's more virtual, like a social network, we need to be able to track the interconnections and how things are related to each other. And as I think a lot of you know, our main kind of weapon in the fight against you know, ever increasing amounts of data is parallelism. You know, graph data raises some interesting challenges for parallelism. And then finally, there's a whole other set of data that's coming from all the infrastructure that we're putting out there, all the smart infrastructure, whether it's you know, sensors or you know, other type of control equipment, or even you know, smartphones and things that people are carrying with them. Okay, and so there's all this chatter going back and forth between all these connected devices, generating huge amounts of data that you know, there's value in. Okay. So, you know, getting the data is one thing. There's lots of it out there. Of course, what you want to do is start to make sense of the data. And this is, obviously, there's a lot of different types of applications, and I'm going to talk about some of the ones we're focused on. But one that's happening actually in this building here is Alex Bayan and his group is working on what they've been calling next generation maps, which is basically a mashup of, you know, data that you collect from you know, people and devices out in the wild, you know, models of the physical world, processes of merging those together, you know, to create new data products, right? So it's not just a question of simply reporting on the data or you know, monitoring it, but you can also create new and valuable things that you couldn't do without this entire pipeline. So, you know, some of the things that they're working on are things like earthquake early warning systems, you know, traffic prediction and measurement systems, things like air quality and noise pollution warning systems, and so on. Okay, and so you know, if you think about what's involved in building some of these applications, you know, yes, there's huge amounts of data. Yes, a lot of that data is messy and incomplete and needs to be integrated and put together. But it's really kind of this whole set of things that you have to do in order to build these new data products. Okay, and it's sort of that large class of, it's the fact that there's so many kind of moving parts here, which is what drove the creation of the AMPLab. So, you know, what are you going to do with this data? Well, all sorts of stuff, right? I mean, that's why people are so excited about this. You know, a lot of what we do, frankly, is reporting. You know, whether it's, you know, scheduled reporting or, you know, sort of ad hoc querying, real-time monitoring and reporting, and so on. you want to be able to explore the data, looking for patterns. You want to be able to dig into the data to find out, what really happened or what's really happening, through many levels of abstraction. In physical systems, you want to be able to do closed-loop control, right? If you're controlling a physical environment, you don't want a person in the loop because there's not time for it. So how do you make that work? And then there's a lot of things we're doing, trying to understand the data at a deeper level. So building models and then being able to use those models for prediction. Okay? So, this kind of runs the gamut of sort of very quick, very time-sensitive analysis to, very deep, construction of models and then maintenance of those models. Okay, so, what I want to do is just tell you a little bit about how we've framed the big data problem in our project, because that's going to be what's underlying a lot of the discussion for the next 2 days. So, a lot of people have adopted this 3V definition of big data. I resisted it for as long as I could, but I've actually found that it works reasonably well. The way we were talking about it was that, it's really a combination of 2 problems. It's the size of the data, right? It's the amount of data that you have. And it's the complexity of the data, the fact that the data is dirty and incomplete and you've got to make sense of it, right? And it's really this combination of problems that makes things really hard. Okay, if you've got a lot of clean, data that's in perfect shape, it's hard, but we know how to make sense of that. If you have a small amount of data that you need to clean up and put together, we kind of know how to do that. So when you put those 2 problems together, right, the complexity and the size, that you start getting into trouble. And in our point of view, we're researchers. We like trouble. So, this is where all the good problems are. So the 3 V's, if you haven't seen it, are volume, velocity, and variety. And so volume is, obviously the amount of data. Velocity is the fact that it's coming at you and you're getting more and more of it over time. And then, the variety is the fact that it's coming from all over the place. And then I'm going to spare you what I've been seeing in a lot of talks lately where people say, oh, but, there's really 5 V's or 6 V's, and they come up with new words that start with V's. But, okay, so that's kind of the source of the problem. But so what? Why is that a problem? You get a lot of data, and it's kind of messy. Why is that a problem? Well, the problem is that you've got a decision you're trying to make, or you've got a question you're trying to answer, and you have a certain amount of time, right? You've got to make that decision, or you need your answer within a certain amount of time. You've got a budget, right, in cost, right? You can spend a certain amount to get your answer. And in order to make your decision, you need a certain confidence in the result, okay? So it's this kind of 3-dimensional space that's really the problem, right? You need to get your answers. You need to be able to deal with all this data within the time constraints, the cost constraints, and the quality constraints that you have for your particular problem, okay? And so what we're doing in the AMPLab is we're building infrastructure that's focused on helping, people and ultimately systems navigate that 3-dimensional space. Okay, so you want to be able to trade off in that space. If you have more time, you can get a higher quality answer, right? If you can spend more money, you can get a faster answer, and so on. Okay, and we want the system to support those kinds of trade-offs and then ultimately be able to help you optimize, within that 3-dimensional space where you are. Okay, so, there's lots of definitions of the big data problem. This is the one that we started with in the AMPLab, right? It's this 3-dimensional problem of time, cost, and quality, all right? And the quality one, by the way, turns out to be the one that changes everything. We've been dealing with time and cost for a long time. There's another way to look at the big data problem, and this comes from Mike Jordan, who's our machine learning guru in the project. And the way Mike's been explaining the big data problem is that, there's kind of 2 ways that data can grow. If you think of data as, say, a table. I'm a database guy by training, so I like to think about data in terms of tables. If you think about growing the number of rows in your table, right, so you're getting more records about more things, that's when algorithmic complexity kicks in, right? So if you've got a learning algorithm that's n squared or n cubed, or in some cases, n to the 6th, what's going to happen is, you give it some data, it runs fine. You give it a little more data, it runs slower, but you get your answer. You give it more data, at some point it goes away and never comes back, okay? And parallelism isn't going to get you out of that problem, right? Because it's not a linear problem, okay? So as you add more rows, you've got algorithmic complexity, okay? And so you got to be able to deal with that, right? You come up with smarter algorithms. that can run faster. You can come up with maybe less accurate algorithms that run faster and so on. And you can trade off in that space. All right, so that's one thing we're doing. The other thing that's a problem is, as you grow horizontally, right? So as you add columns to your table, you have more problems, right? So as you start collecting more types of information about the things that you're collecting information about, what you end up with is an exponential explosion in sort of the number of hypotheses that you can make over the data, right? Is it, column A and column C and column D that are causing this to happen, right? And, with enough data, you're going to find evidence for pretty much any one of those hypotheses that you care to pose just because of pure randomness. And so you got to be really sensitive to the statistical properties of the data and the statistical properties of the answers that you're getting and the quality of the inference that you're making. So the way Mike's been formulating the problem, which I think is a pretty useful way to think about it, is really at the top of the slide that what you want is, if you get more data, you want better answers, okay? And with these two problems, that's not what happens, right? In the current state of the world, if you give the system too much data, you don't get any answer, okay? And if you collect more and more information about more and more things, you start seeing all sorts of weird random effects, and so the quality of your answers goes down there too. And so what you'd like is, given an inferential goal and a budget, right, because that's part of our three-dimensional space here, you want to guarantee that the quality of the inference increases monotonically as you get more data, right? So as you get more data, your answer doesn't get worse, and hopefully it gets better, okay? And it does so within the time constraints that you have, okay? And so in other words, we tend to think of data as a load on the system, but actually it should be a resource, right? You should get, a resource is something that when you get more of it, you're happier, right? And we should be happier when we get more data, okay? So that's another way of posing this big data problem, okay? All right, so that's how we frame the problem. Let me tell you how we're attacking it. So our view is that if you want to make sense of a bunch of data, you've got sort of three basic classes of resources to use, right? You've got algorithms in the sense of statistical processes, machine learning, business intelligence processes, and so on. Okay, so that's the algorithm side. You've got, ever and ever more scalable machines, right? So cloud computing, private cloud, public cloud, whatever. That's the machine part, this ability to sort of harness, warehouse scale computing, if that's what you need to do. And then, the thing that we hit on that's really resonated with a lot of people is the P part of the project, which is people. So, people need to be involved in, or at least can be involved in sort of the whole process of making sense of data. You can crowdsource data, so people can collect data. The information we're collecting in a lot of applications is actually about people. The ultimate users of our systems are people. Okay, so what we want to be able to do is build an infrastructure that lets you blend these three very different types of resources, again, to solve our big data problem. Okay, so if throwing more machines at a lot of data with a simpler algorithm is the right thing to do, we want to be able to do that. If bringing people in through a crowdsourcing environment to help make sense of some of the information that the algorithms can't quite understand, if that's the right thing to do, we want to be able to do that. And we want to be able to do that on the fly for the given problem that we're trying to solve. Okay? So that's our long-term vision, is a system that seamlessly blends algorithms, large-scale computing, and people, individually and in large groups. Okay? So that's the AMPLab. That's the AMP project. Why are we doing this now? Why is this the right thing to be doing now? Well, we believe, there's been a huge amount of innovation in the big data space and in data management software over the last few years. And, we're excited about that, and we're working with those systems and trying to use them as much as we can. But even if you look at, if you step back and you look at sort of the latest, greatest, what people sometimes call NoSQL environment, and you compare that to, say, a database environment, which is a SQL environment, the places where those things came from are really not that different, okay? And at a layer point of view perspective, they're actually not that different. And we think that you need a new approach, right? We think what you need to do is take machine learning, computer systems, and databases and put them all together and sort of rethink those boundaries, okay? and rethink how you put systems together with those capabilities. Okay, now, that might not sound so radical, or maybe it does, but in a university environment like where we are, these groups tend to be very siloed. Okay, and there's not a lot of collaboration in most places. So we set out to really build a project where there was deep collaboration across these three areas. Okay, and so as I'll tell you in a bit, we've gone so far as to put everybody from these different groups into a common lab space so we can all work together. We also think it's a great time to just rethink the design, the fundamental design. So we're doing our work in the university setting. Why are we? This is such a practical problem. Why are we doing it as opposed to industry? We think we can afford to take more chances, right? Because our whole business is trying to push the envelope. Okay, and even if our systems end up not being exactly right, we know we're going to come up with great ideas. We know we're going to put out great students. We know we'll get our papers and so on. And so we can afford to take this chance, and that's why we're doing it. And we've got a lot of companies that we work with who are willing to, come along with us on that ride and kind of maybe let us push the envelope a little bit, or at least in some different ways than they are. So it's a great opportunity, right? There's a lot of demand for low latency. That's going to require new approaches. This ability to trade off quality versus our other resources is really important, and people are more accepting now of sort of, probabilistic and answers with error bars on them and so on. And then just this ability to have elastic resources through various types of cloud computing is a great opportunity. And then the fact that crowdsourcing is really taking off, and there are platforms now where you can get access to huge groups of people to help you do work is something that didn't exist when a lot of these SQL and NoSQL stacks were designed. And so we think it's a great opportunity. There's a lot of opportunity for creating something new, and there's a real reason to try to do it. Okay, and so that's really the motivation behind our project. So let me tell you a little about the project, and then we'll move on. Because we come from these different areas, we've got a pretty large group of faculty that are involved. We've got 3 directors of the lab. Myself, as I told you, I come from a database background. Jan Stoika, who you're going to hear from in a couple minutes, is a system and networking guy. Mike Jordan, who I mentioned earlier, who's currently on sabbatical, is our machine learning guy. And the 3 of us sort of, try to oversee the direction of the lab. But there's, 10 faculty that are working on the project, plus a bunch of other people that I haven't listed here that are involved from a bunch of different areas. We've got an amazing group of, students, postdocs, visiting researchers, the best people in the world, come to work with us on this. And so, it's just really a great group. And, we're organized, as I mentioned, to take these people who come from sort of different ways of thinking, different intellectual backgrounds and traditions, and, we put them together, and we put them together a lot. And so, as I mentioned, we have, if you have some time later on today, you can go over and see the lab. It's across the street in Soda Hall. It's nothing special. It's just a big open space like a lot of you guys probably work in. The thing that's different is we have people from all these different sub-areas working together, and including the faculty and the students and the postdocs and everybody sitting in the same space. So it's highly collaborative. And the other thing that's important is, we work very closely with people in industry. A lot of you guys here are from our sponsor companies. I'll tell you a little bit more about how we work with companies in a second. But Amazon Web Services, Google, and SAP sort of made large commitments to us to help us get started and provide a solid base. We've got, I lost count now, 14 other companies that are working with us, that are helping to support the work. And you can see there are people from all over the world, different industries, big companies, small companies, new companies, old companies, so on. It's really a great group of support, and we get a lot of benefit from working with all these companies, and we hope it's mutual. I'll also mention we've gotten some federal funding lately, and I'll talk about open source in a second. Okay, so it's a 5-year project. A year into it, we got a 5-year grant, so now it's a 6-year project. But that's kind of the time frame we're talking about. So the grant we got, some of you might have seen it. The White House announced at the end of March, I believe it was, a big initiative trying to get people in research places, especially universities, to start thinking about big data. Well, guess what? We had been thinking about big data for a long time at that point. We had a submission for something called an Expedition Grant into the National Science Foundation right at the time that this announcement was coming out. And luckily for us, we ended up getting to be part of that. We were actually one of the main announcements that the NSF made as part of the White House announcement of this big data effort. So we got a 5-year, $2 million a year expeditions project, which is great for us because it provides us, kind of a solid base of funding for the students in the room. Most of you are going to do 5 years of research or so to get your PhDs, so it works out pretty well. But what we liked about this was that they acknowledged that our approach of combining machine learning, cloud computing, and crowdsourcing, the A, the M, and the P, was kind of what was really unique about what we were doing. Okay, so we're a big part of this. There's also DARPA, which is the Department of Defense, has an initiative going on big data, and we're going to play a large role in that one as well. So we're involved there. With industry, just quickly, the way we work with industry, a lot of you guys know this, is we work very closely with people in these various companies twice a year, once in the winter, once in the spring or summer. We have a 2.5-day off-site retreat. In the winter, we go up to Tahoe and get an afternoon of skiing in. In the spring, we go out to the coast somewhere. But most of it isn't fun and games. Most of it is deep dive presentations. You'll hear some similar things over the next 2 days. But presentations mostly from students and researchers about what they've done, what they're doing, where they're going. We have a formal feedback session where all the sponsors tell us what they liked, what they didn't like, things that they think we should be doing or putting more emphasis on. And we take that advice very seriously because people in industry see a lot of things that we don't necessarily get to see on our own. And just as an example of that, AmpCamp happened because at our last retreat, a number of the sponsors said, hey, you guys really need to package. You guys have been releasing all this great software. We need a single place to find out how to use it. You guys should put something together. And that's exactly where this meeting started. Okay, so it's a really valuable input for us. There's opportunities for internships. A lot of our students go off and do that. Obviously, you build relationships over time, and there's hiring opportunities. And our key thing is that all the stuff we're doing, people ask me, how do you work with 17 companies? I mean, how do you manage all that IP? And the answer is we don't. We do everything in the open. We release all our software, BSD or Apache. We publish everything that we can publish, and that openness lets us move really fast, okay? And that's how we work with all these different companies. All right, so let me just tell you briefly, you're going to hear more about this from Jan. The thing that we're building, right, we're producing a lot of research, but ultimately what we want to produce is a system that we're calling the Berkeley Data Analysis System, BDAS, or we pronounce it BADAS. And you'll hear more about it. The things I just want to point out is, our resources are data, machines, and people, okay? And a big part of what we do in order to be able to make this time, cost, quality trade-off is we have to understand answer quality and confidence throughout the whole system. And so Jan will talk a little bit about that, how we're pushing, notions of data quality and answer quality throughout the whole system. But, and then you'll hear over the course of the 2 days, how the machine learning needs are driving the design of this stack. But the thing that we're mostly going to be talking about during AmpCamp are our initial pieces that make up this badass software stack. And eventually we're going to keep building it up. You'll hear more about that, okay? And so that's the main thing we'll be focusing on for the next 2 days. I just want to talk briefly about applications because a big part of what we do is driven by applications. And so I'll just mention these 5 here. Mostly done with people on campus. So we're doing participatory sensing with Alex Bain, whose project I mentioned earlier. We're doing some stuff with Ken Goldberg, who's also in this building, on collaborative discovery, right? So crowdsourcing in some ways. We work with the urban planning guys on a project that they're doing, fusing data from lots of different public and private sources and then using that to model urban environments and understand how they change. We've got a big effort going on in cancer genomics leading towards personalized medicine. I'll mention that just briefly. Actually, I probably won't. I don't have much time. We're doing that with folks at UCSF as well as UC Santa Barbara. And then, a project with the local internet security guys as well. Okay, and if you look at this set of applications, right? Here are the things that we want to be able to handle, right? We want to be able to handle a lot of data. We want to be able to take data from lots of different places, right? That's data integration. Sometimes we bring people in, that's crowdsourcing. Sometimes, we have applications that are computationally intensive. Sometimes we have real-time requirements, physical sensor data, text, unstructured data. And, none of those applications has all of those, but if you take them as a whole, we get really nice coverage of the space. And what you'll notice is all those applications, they weren't private applications. They're all things being done at the university. So we have access to the code, we have access to the data, we have access to the people who are actually the domain experts. So that's why we've done it. So I was going to tell you a little bit about the cancer app, but I think I'm going to skip that until later. Basic story here is that the cost of gene sequencing is going down, 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 down. That's leading to lots of data. That's leading to some really tremendous opportunities for breakthroughs in helping to cure cancer, as well as helping to target treatments directly at individual patients and their individual tumors and so on. So that's, if you're interested in that, talk to us about that. Dave Patterson had a nice article in the New York Times at the end of last year about why he feels strongly that computer scientists should work on this problem. And he basically put his money where his mouth is. This is where Dave's been spending a lot of his time on the AMPLab project, is on starting up this cancer genomics project. Curing cancer is important. Another big problem we have is battery life on our cell phones, right? So another app that some of you might have heard about was an app we released called Carrot, which basically is, I mentioned it, you'll hear about it tomorrow, but it's sort of the quintessential AMP application. It crowdsources information from hundreds of thousands of cell phones about what applications are running, how they're using the batteries, and so on. It brings that into the cloud. It uses Spark, running currently on Amazon. Builds models of normal behavior and abnormal behavior, and then uses that to return back to individuals recommendations on what they should do to extend their battery life. And as I mentioned in the previous slide, we've already had over 300,000 downloads for that, for an application that came out of the lab. All right, so good. So I just want to say, I'm going to turn it over to Andy Konwinski in a second, who's going to tell you how the rest of the days are going to go. But just for more information, if you haven't seen it yet, we have a pretty comprehensive website. It's got a lot of information about the projects, and we try to keep it fresh and updated. There's a very active Spark users group and monthly meetups in the Bay Area. We had, I think, about 80 people at the last Spark meetup. You'll hear more about that. And then, the code that you're going to hear about over the next 2 days is available. It's on GitHub. Some of it's in the Apache process and so on. Okay? And so with that, what I want to do now is invite Andy up. Andy is the guy who's really put this AMP camp together. He's been corralling, herding all the cats to get this to work. And so he's going to give you an overview of what we're going to be doing over the next couple days.